The work done on a particle of mass m by a force k times x upon x squared plus y squared raised to 3 by 2 I cap plus y upon x squared plus y squared raised to 3 by 2 j cap when a particle is taken from point a comma 0 to another point 0 comma a along a circular path of radius a about the origin in the xy plane is 2 pi k by a, pi k by a, pi k by 2a and 0. What are we asked to find? Work done. Work done is what we want to find, and we know the formula for the work done. It is dot product of force and displacement. Okay, it's dot product of force and displacement. Acha, so do we know the force? Yes, we know the force. Okay, it has a very long expression, but please understand that the particle is being taken along a quarter circular arc. Okay, the particle is being taken from a along a quarter circular arc from a comma 0 to 0 comma a. Okay, now the problem's options themselves suggest that this particular force is a conservative force. Okay, why can I say that? Because see, even if I choose this path in the first quadrant to take the particle from a comma 0 to 0 comma a, I would get a value for the work done. Same value I should get, whether I will get in this case, if I let the particle, if I take it from x-axis, fourth quadrant, negative y-axis, third quadrant, negative x-axis, second quadrant, and then positive. Okay, so the work done is independent of path. Acha? Okay, so you got it. Secondly, no matter what point I choose on this circle, no matter what point I choose on this circle, what is going to be the value of x squared plus y squared for that? Is it going to be the same? Yes, it is going to be a squared because a standard equation of circle. So I can now re-modify the equation of the force as k upon a cube into bracket xi cap plus yj cap. Tell me if you understand this.
Yes, sir.
Right, x squared plus y squared is a squared's root is a and cube is a cube. Okay, fine. Now clearly the direction of the force is not the same everywhere. Okay, it is a scalar multiple of r bar, position vector. Okay, it is scalar multiple of r bar, that's position vector. What does that mean? That means at this point the direction of the force is in this direction. At this point the direction of the force is in that direction. Okay, so therefore we have to use integration. And we have to be clear about it. Why are we using integration? It's not because the formula tells us. If it is not required, we will not do it. Okay, so we say as the direction of force changes, we use integration. Rather, we have to use integration. Okay, so we cannot use f bar dot r bar, so we have to first consider dw as f bar dot dr bar. Okay, we have to consider f bar dot dr bar. Okay, now look, if r bar is xi cap plus yj cap, what will be dr bar? Can I say that it is dx I cap plus dy j cap? Yes, can I say that?
Yes, sir.
Yes, so elementary work dw can be equal to, now look, dot product will give k by a cube as it is, k by a cube as it is, x dx that's y dy. Do you follow till this? Yes. F bar dot dr bar is, look, this is x I cap. Yeah, you got it, dx I cap. So dot dot, that is y got it. Okay. Now because this is path independent, I can say that the net work done is equal to k by a cube into integral of, now look, x is decreasing from a to 0 and y is increasing from 0 to a. Now because in definite integration, the variable of integration is a dummy variable, x dx's integral and y dy's integral will be same. But because we have flipped the limits, we can use the property of definite integrals to finally arrive at the conclusion that the net work done will be 0. Do you agree to this? If you don't, then you can integrate. Well, I've used this property. Two of them rather. First property is this. Do you get it? In indefinite integration, variable of integration is a dummy variable. So it could be good. This first property. Second property is this. If you flip the limits, the value of the definite integral changes its sign. Got it? Yeah. So y dy can be made x dx. And limits can be flipped by changing the sign. So x dx a to 0, x dx a to 0, this is positive, that's negative. So 0. Clear? Clear. Okay. There is one more thing here, which if you had noticed, we would not be required to integrate. And that's this. Although the direction of the force always changes, the force remains radial. What is it called? The force remains radial. Correct? The force remains radial. Now look, this is always going to be a circular motion. Do you agree? This is always going to be a circular motion because it never leaves the circle. Okay? Now, understand that if force is always radial and the displacement is always tangential, for a circle the displacement is always tangential. So no matter where the particle is, force is radial and the displacement is what? Tangential. So force and displacements will always be perpendicular to each other. Please follow this, or if you are not understood, please ask me. What I'm saying is, I'm saying, yeah, you understood. F bar remains perpendicular throughout the particle's journey from a comma 0 to 0 comma, no matter where you are on the circle. So dr bar, because it is always perpendicular to f bar being radial, the integral will be 0. Is that clear? So that is a smarter way to solve the problem. What is it? As particle remains on the circle, as the particle remains on the circle and the force is always radial, F bar remains perpendicular to dr bar. Therefore, F bar dot dr bar will always be 0. In other words, in circular motion, work done by centripetal force is always 0. Okay.